Okay, everybody, we are making this video because we had terrible trouble with fourth period being able to have some connectivity. So the things that I have started are going to be things that are going to be really important to you to make sure that you use. So first we have some terminology. Original substances before the reaction are known as the reactant. Resulting substances are known as the products. In chemical reactions, we have to show them or write them using symbols, subscripts from formulas, and coefficients to show the number of reactants and products in a reaction. All right, so those are some new terminologies for you. Some old terminology is evidence of a chemical reaction. Here we are going to observe a chemical reaction if a gas is formed without boiling, if there is an unexpected color change, if energy is used or produced. In other words, if we produce some light or we produce some heat or there is a sound. Or finally, if mass of one reactant is actually gained by another reactant. In other words, there's a mass change. So those are some old pieces of information. Now we're going to add to some new pieces of information by talking about some formulas that you are going to need to make sure that you memorize. Because you are going to have to make sure that you do these and use these. And these are called the diatomic elements. There are 7 of them, and you must memorize them. In fact, when it says hydrogen, or hydrogen is produced, or hydrogen is used, or nitrogen, or what have you, then you're going to remember to always write them as H with a subscript 2, or N with a subscript 2, and so forth. These are called diatomic elements. In other words, they're made of 2 elements single bonded together. In the case of oxygen, it's actually double bonded, and nitrogen, that's actually triple bonded. But they are 2 atoms bonded together. And you do have to remember these. So I often use the terminology of I for iodine, hate, H for hydrogen, FN as in FN, broccoli, B-R-O and C-L. So just trying to have some funny way of trying to remember it. So it was I hate effing broccoli. Okay, so if you need to pause me so that you can get your notes written down, please do. So then we go on to, okay, well, what symbols are we going to use? And so our first 2 symbols we are going to use is first the coefficient. This is a number placed in front of a chemical formula to show how many moles of that substance are in that formula or in that equation. Then we use an arrow pointing to the right, meaning yields. Synonyms for yields are makes, forms, or produces. Remember to pause me if you need to get some time to write stuff down. All right. Other symbols that we are going to use are double-sided arrows to indicate a reversible reaction, a small s to indicate a solid, also known as a precipitate. That is terminology that you will hear again. That's why I circled it. I'm going to put a star next to it. It is tested, so you'll need to make sure you remember precipitate means solid. If I have a reactant or product in the liquid state, we will use a little L. If I have a reactant or product in the aqueous state, then that means that it has made a solution. In other words, it has been dissolved in water. So we use AQ in parentheses. If I have a reactant or product in the gaseous state, then we are going to use G. If we have to heat something, then we are going to use a triangle, or if we have to say the exact temperature, we show that over the arrow. If we have to do the problem or the reaction under pressure, we use the actual pressure we used. If we have to show a catalyst, a compound that makes the rate of the reaction speed up, then we're going to write that formula over the arrow. So in this case, I used platinum. It is a common catalyst. And finally, if we are going to electrocute a reaction, then we are going to use the letters ELEC to represent electricity being added. We are going to go ahead and start with our first reaction, and our first reaction has to do with our Bunsen burner. So the first thing that we're going to do is I'm going to get everybody's Bunsen burner lit, but I'm going to go ahead and light mine. So right now I have turned on the gas in my Bunsen burner, and I got to make sure that I can make this work. It's much harder to do when I've got on my gloves. There we go. I don't know if you guys can see it, but there is my gas. Let me see if I can turn it around. There is my gas right there. And I can tell you for sure that that gas flame is way too tall, so I'm going to lower my gas flame right there. You can look at that real quick while I am showing everybody else how to light their Bunsen burner. Is you want to be able to see a flame, and I'm going to try to put my hands around it, that you can see the outline of an inner cone that's upside down. Can you see an outline of an inner cone that's upside down there? Okay, so I know that the people at home can see this. Mubarak, let's bring yours back just a little bit. Now can you see the outline of the inner cone inside there? Okay, so that outline, the very tip of the top of that inner cone, Zane, yours is kind of like right where that first yellow is right there? Okay, and yours is a little bit too high. I'm going to bring yours back a little bit so you can see. There, it might be easier to see the inner cone now. Okay, that very top of that inner cone, that is the hottest part of the flame. So that is what we're actually going to use for our second reaction. I'm going to go ahead and turn on the lights. But for right now, we need to go ahead and write in the symbols for just this reaction right here. So this reaction, and I'm going to move this to the side. This reaction, and I'm going to bring this back down so we can all see it. This reaction, what we saw on our observations, and you're going to go ahead and type these in, we saw a blue flame. We saw an inner cone, which we just learned is where the hottest part is. And we could see that it was hard to see. It's sort of clear, sort of a clear flame. Zane, you have a little bit of yellow in your flame, and you can go ahead and put that in your observations as well. Okay, so now we're going to write the equation for what it says. The first thing it says is that methane burns in air. Okay, so I'm going to tell you guys the formula of methane is CH4, and it was delivered to our Bunsen burner with the cord or the hose here. So this was CH4 gas, and it had to be in air so that it could have oxygen around it. So that means we're going to add a plus symbol. So CH4 plus some oxygen. And oxygen, we have to remember, is one of our diatomic molecules. So we have to show it as O2. And then, of course, since oxygen is also a gas, we're going to put a little G next to it. Okay. It combines with oxygen, so we just did that. And then we have the words to produce. That's where our arrow is going to come in, to produce. And it says we're going to produce carbon dioxide, which we all know is a gas. We can confirm that just by breathing out and recognizing that's carbon dioxide gas. And it is also producing some water vapor. And vapor is another term for gas. So we have written our first chemical equation there. So that's pretty cool. Let's set our notes to the side right now, and I'm going to bring back my flame. And I'm going to go ahead and raise this up so you can see my flame, and I'm going to turn mine around so you can see it straight up. Okay, so I'm going to demonstrate this first, and then you guys are going to get to do it. Okay, so this, let me get it, there it is. That is a piece of magnesium. It is a whitish, silverish metal, okay? And I'm going to make sure that I put my watch glass right near it on the tabletop so that I can have a place to place my watch glass after it does its thing. So this reaction says, when heated in oxygen, and I'm going to hold it like this with my tongs, when heated in oxygen, magnesium becomes magnesium oxide. So let's see what this does. To make this work, I have got to place my magnesium in the hottest part of the flame. And remember, that's at the top of the cone. So here I go. I'm going to try to get it into the hottest part of the flame. And you'll know when I've gotten it there. Do you guys see how bright that is? That is very definitely some light that was given off. Okay? And what is left here is a white powdery substance. Okay, so I'm going to show everybody else and let everybody else do theirs right now. Okay, so let's take a moment and go ahead and write about what we just saw happening. And I want to show you what that looks like. It's some of it's burnt, and the part that is burnt actually made a white powder. And you can tell the part that did not burn, it's still a silvery sort of gray piece of metal there. So that's what we got. So observations we can write down is magnesium is silver, and magnesium oxide is a white powder. All right, what was the other main observation we had from this reaction? Bright white light. Bright.
Can you repeat what you said at the beginning?
About the observations?
Yeah.
Okay, I said that magnesium was silver and magnesium oxide was white. To write out this equation, I'm going to write magnesium, which was a solid, plus some oxygen, which I know has to be O2, and we know that oxygen is a gas, and O2 has to be O2 because it's one of our diatomic elements, and that we had to form magnesium oxide, and I have to make sure that I write it correctly using my charges, so I have Mg plus 2 and O minus 2, so the 2's cancel out, and I'm left with MgO. That is my next example of a chemical reaction. Since this was heated, both of these first two reactions can have a triangle over the top of them. For my next reaction, we are going to use some hydrogen peroxide. And you will notice that the hydrogen peroxide we use in class is 30% hydrogen peroxide. That's 10 times more concentrated than the one that you use at home. So I'm using this so, of course, we get to see a good reaction. And I am going to place some hydrogen peroxide on my watch glass here. So I'm going to get a dropper and put in some hydrogen peroxide onto my watch glass. And here is the hydrogen peroxide. And you'll notice right away that hydrogen peroxide is a clear liquid. So that's one of our observations. Hydrogen peroxide is a clear liquid. Now, did you guys all notice that hydrogen peroxide is in a dark brown bottle? And that is because hydrogen peroxide is more likely to react by decomposing or breaking apart when it's in the sunlight. So that's why it's kept in a dark brown bottle. And that means right now it is currently decomposing, right now. But we can speed this up through the use of a catalyst. And the catalyst we are using, and let me show it to you on screen, the catalyst we are using is potassium permanganate. And don't worry, we're going to write all this down. Potassium permanganate. And so I'm going to get a little bit of potassium permanganate, which you may or may not be able to see, but it's kind of a dark purple color. Okay, so I'm going to use 2 drops. Actually, I only needed 1 drop. And you might notice that that really sped up the reaction, and it really did. If I feel underneath it, you find out that it's really quite warm underneath it. Okay, so that was our chemical reaction to form water vapor, that was all the steam you saw, and oxygen gas, which you can't see that. That's a gas we can't see. So that is our third reaction. Okay, everybody, so for this next reaction, what we just saw was we saw some hydrogen peroxide, H2O2, and that was definitely a liquid. And we used a catalyst called potassium permanganate to help it decompose very quickly into water vapor, which was the steam we saw, so it's a gas, and some oxygen gas. We have to remember oxygen is always diatomic. Okay, now let's talk about our observations we saw. We saw that the H2O2 was a clear liquid, and we saw that the KMNO4 was a dark purple. All right. What we noticed when we put the catalyst into the hydrogen peroxide is we saw steam, lots of bubbles, and we felt some heat being produced. So those were our observations for the hydrogen peroxide. Okay. All right, so my next reaction, it says that we are using lead 2 nitrate. We are actually going to change our lead 2 into silver because my lead 2 was not working. So we're going to use silver nitrate instead. So for this reaction, I'm going to put some silver nitrate on my dish. And there's my silver nitrate right there, and I'm going to use all of it up. And then I'm going to go ahead and add to it some drops of potassium chromate. That is the other reactant. And so I'm going to go ahead and put in potassium chromate. And I'm realizing that I did them out of order, but that's okay. We'll do them out of order for both. And I did 2 drops. Do you notice that what we made was a bright or brick red color that you can no longer see through? So while this was a clear liquid before, now you cannot see through it anymore. You can't see the part that's over my hand. You can't see that. It is not producing any heat. It's still the same color, but it's the same temperature, but you can definitely see, especially if I hold my hand under it, that there are some solid pieces forming. So the reason you cannot see through it is because a solid is forming. Okay, so we are going to write about this as well. Okay, and I'm just realizing that we got things out of order, but we'll fix that. I just realized that I did my examples out of order. We will come back to this example. The reaction that we just did is actually on the next page, and this was a solution of silver nitrate and potassium chromate. The observations we saw was silver nitrate was a clear solution, and potassium chromate, CrO4, there we go, was a yellow but a clear solution, and what we ended up with was a brick red solid forming inside a clear solution. That's what we ended up seeing. Okay, so let's talk about our chemical reaction. We have a lot of ions going on here. We have some silver ion, and it is reacting with some nitrate or crisscrossing with nitrate, so we end up with AgNO3 because those charges cancel out. And we already said this was a solution, so we're going to use AQ. And we added it together with the potassium chromate, and that was K1 plus being put together with CrO4 2 minus. The charges do not cancel this time, so I end up with K2 CrO4. That was also a solution. It was a clear yellow solution. Now, once those two things were put together, they yielded or produced the silver chromate. So that means I'm going to put together silver and chromate, and again the charges won't cancel, so I'm going to end up crisscrossing, and I'm going to get Ag2CrO4, and that was the one that formed the solid. And the other solution, the clear solution around it, and just so that you can see it and remember it, that's what we have. That's what we're looking at right now. We definitely have some solid in there, and then we can see some clear solution around it. And for those of you going, where's the solid? Now can you see the solid a little bit better? Okay, so that other solution is going to be potassium nitrate, and both of those are 1 plus and 1 minus. So we end up with NO3, and that we use AQ for that result. Okay, so now we do need to go back and do that one more reaction that we skipped over a minute ago. The final reaction that we still need to do is one for where we're going to use silver nitrate and sodium chloride, and what it's going to produce for us is solid silver chloride and sodium nitrate solution. So that's what we're going to try and see if we can see. So this is my cleaned up dish, and I'm going to go ahead and add A good full dropper of your sodium chloride. Please go ahead and add a full dropper of sodium chloride to your dish. And it just looks like, I'll bring some more to you. Okay, then we're going to add a few drops of silver nitrate to our sodium chloride. So go ahead and use your dropper, and we're going to drop a few drops of silver nitrate to our sodium chloride. Now those at home, you can probably see right away that this is forming something cloudy and white. So right away you might be going, that's forming a solid, and the solid that forms by your description is the silver chloride. Now you might be going, okay, where's the clear liquid part of this? So you might be able to see that actually that there is clear liquid over here, and there might be some clear liquid around it. If we let it sit for a little bit, the solid particles will settle to the bottom, and you'll be able to see the clear liquid over the top of it. Okay? So that is our reaction. Okay, so what we just saw was that our silver nitrate, which was a clear solution, so AgNO3 was a clear solution, and sodium chloride was a clear solution, and we produced a solid that was white, and as I told you, that was silver chloride. The other clear solution produced was sodium nitrate, and so we'll go ahead and record sodium nitrate being the one that is produced. So let's write this out as a chemical reaction. We had, how did I figure out it was AgNO3? Because I used the ions Ag1 plus and NO3 1-, and I see that those two cancel each other out, so I do not need to, let me fix that, there we go. So I do not need to crisscross them, so I'm simply going to write them as AgNO3. And that was a solution to begin with, so I'm going to use AQ to represent an aqueous solution. And since we added it to the sodium chloride, I'm going to put a plus symbol. To figure out sodium chloride, that is going to be Na1 plus and Cl1 -. So again, my charges cancel, so I have Na, Cl, and that was also a solution, so I'm going to show it as AQ. And then we formed that white solid, which was AgCl, and that came from the combination of two ions, Ag1 plus and Cl1 -. So I got AgCl, but this one made that solid, so I'm going to put an S next to it. And finally, the other solution that was produced came from the combination of the two ions Na1 plus and NO3 1-. So I end up with NaNO3, and that was a solution, so we write that as aqueous. And I was trying to let this sit for long enough for you to be able to see. Can you see just a little bit of solid starting to form here? I think maybe you can see it. I'm swirling it around so you can see it starting, the solid pieces starting to form there, and that the other solution actually is more of a clear solution. So I have some solid and I have a clear solution. So there's what that looked like. Okay, so your homework tonight is to complete a homework that looks a lot like this. Try your best. I know that this is going to be confusing and hard. I still want you to try your best to write out these equations. Once you get done writing out these equations, please submit it. Even if it's wrong, it's going to be okay, because what I'm going to ask you to do is peer edit someone else's equations and give them some feedback. And I'm going to be grading you on how well you give feedback. If you don't turn in a page, I cannot give you a grade for feedback. So keep that in mind, and please do the homework that is on the next part of the module. Thank you very much. Have a great day, everybody.